Hi everyone, my name is Rebeckah Fussell.
And I'm Alex Wikner.
And we're going to be talking about how you can make a good prediction with a bad model, a machine learning approach to forecasting chaos.
Oh wait, that's good.
So the problem we're looking at is predicting dynamical systems, in particular complex and chaotic systems like the weather. So this is of course a very important problem, also a very difficult problem. Chaos is difficult. But we hope that the solution that we propose today may help improve weather prediction. So the actual system we're looking at is easier to manage than actual weather data. We're looking at a simulated system based on the Kuramoto-Sivashinsky equation. So this is simulated data, but it is spatiotemporal and chaotic, much like weather. We represent data from this system in plots that look like this, with time on the horizontal axis, one dimension of space on the vertical axis, and the color axis represents some variable u. Now, this equation, we know, because this is a simulated data, we know that this blue equation completely expresses everything that's happening, all the dynamics.
So the main issue that we have when we're trying to predict a chaotic system is this kind of butterfly effect. So you might have heard this before in describing that, if a butterfly either chooses to flap or not flap its wings, it can have huge changes on things like the weather, causing things like a tornado a long time in the future. And that's sort of describing what happens in a chaotic system, where when you have nearly identical states, they're going to diverge exponentially from one another over a characteristic time scale in Lyapunov time. So we can see this happening if we go and look back at a couple plots of that Kuramoto-Sivashinsky equation we saw before. So here we can see that we're looking at the true evolution of the system with the function we're plotting over here on the color axis. But if we go through and we change one measurement of that system with just a 1% error, so you can think of this as a butterfly flapping its wings, we see that we're getting some pretty significant changes in the dynamics after a pretty short amount of time. And we can see this even more clearly if we then go and look at the difference between these two plots. So here the green is representing where they're pretty similar, so it's fairly accurate, and the not green is representing where they're not accurate, where they began to diverge. And we see that the black line denotes around where this prediction is beginning to fail, and it happens after around 4.5 of these Lyapunov time units.
So a typical approach to predicting this sort of system is to look at the underlying mechanisms, write some equations, and build a model. So here, if you remember, this blue equation completely describes the dynamics of everything happening in our simulated system. Realistically, we wouldn't know everything happening, so to adjust for this, we have some error in our approximate model that we describe with this term. Now, this sort of model-based prediction can really work. The issue is because of this error and with the butterfly effect, your model-based prediction may diverge before you even really get an acceptable prediction.
So the other way that people have thought about trying to predict these kind of systems is through a technique called reservoir computing. So this is a non-model-based technique that is only going to use the data that we've taken from our either real life or true simulation. So what we want to do is we want to train a recursive neural network to understand the dynamics of the system and predict later in time. So just to quickly show you how this works, we begin with the state of our system that we know exactly from our experiment or from our true simulation. We feed that into an input layer that is going to couple this into our reservoir computer or our recurrent neural network. Now, once we do this for a lot of different states of our system, we're going to get a lot of different reservoir states from these reactions. And what we want to do is then go and adjust this output layer here such that we can map our state of our reservoir using the output layer to the next state of the system over here. Now, the reason that this is able to work is because this reservoir essentially acts as a very high-dimensional dynamical system that is going to react in a fairly unique way given these different types of inputs. And we also have a lot of different parameters that we can go and tune in our output layer here to allow us to make this connection. Now, once we've done that, we can flip this switch right here into the prediction phase and allow this thing to sort of loop back on itself and predict later in time. Now, another issue that I should just point out is that these can be extremely computationally expensive methods, especially for things like weather prediction, because you need to have a reservoir that is large enough to be able to forecast the dynamics, and typically that means that the reservoir is going to be prohibitively large for you to actually use this method.
So our work this summer was in building a prediction method that combines these two to hopefully overcome some of these downsides to both methods and make better prediction. So this is our hybrid prediction method. We still put in past data into the input layer, but we also put in model-based prediction into both the input layer and the output layer, so that then when we move to training, so when we move out of the training phase and into the prediction phase, the model-based predictor is already giving the output layer some idea of what's happening, and the nodes can focus on adjusting for the error.
Mm-hmm. So we can see the results of what happened here. So these are the plots of the true evolution of our Kuramoto-Sivashinsky system minus the prediction. So this is just like the difference plots we saw before. So you can see that for a good model, so something that has a very low error, and for a large reservoir, or something that has a lot of nodes and a lot of connections, so very high dynamics, or high dimensional dynamics, we can see that it's predicting for around 2 Lyapunov times, whereas the hybrid method is able to predict for around 7.
And perhaps one of our most exciting results, we see that the hybrid gives a good improvement to the prediction, even in cases where the reservoir is small and the model is bad. So you can see in this case, neither is really making any sort of acceptable prediction. However, in combination, the hybrid is doing better than even the good reservoir on its own, the good model on its own.
So in conclusion, the hybrid is able to outperform each of its component methods, and in doing so is able to reduce computational expenses by allowing us to use much smaller reservoirs, and is able to increase model viability by allowing us to use models that might not be able to predict it all on their own. So the next step in this is, of course, applying this to weather prediction, and in doing so, we want to be able to apply this to some different real-world systems or experiments, and to possibly use a parallel multi-agent approach to be able to apply this to much larger systems with parallel computing resources.
So we encourage you to come visit our poster. We'll go into more detail about our methods and our results, and look at another system as well. So thank you.